ladies and gentlemen, and esteemed participants and distinguished guests. So good morning or good afternoon, depending on where you are. And warm welcome to the international webinar on Earth Observation for Agricultural Statistics, brought to you by the collaboration between the Africa Regional Hub on Big Data and Data Science, that is supported by the National Statistics Institute of Rwanda, the African Center of Statistics, and the Office of National Statistics of the United Kingdom. So today, we are embarking on a journey that underscores the very important role that Earth observation, big data, and cutting-edge statistical methodologies in advancing sustainable development in Africa. The importance of this webinar cannot be overstated, and it focuses on a subject that is central to our continent prosperity, which is agriculture. As you know, agriculture is a backbone of many African economies, and it is providing livelihood for millions and ensuring food security for our growing populations. However, it faces multifaceted challenges from climate change, resource constraints, natural disaster, and even the evolving market dynamics. Therefore, harnessing the power of Earth observation and data-driven statistical analysis becomes not just an option, but an imperative for achieving our development goal, particularly the United Nations Sustainable Development Goal. Therefore, our objective today is to shed light on how innovative tools such as the Earth observation data cubes, smart classification,
Good morning, Gao.
Hi, good morning. I'm okay now.
Hello, all is good, all is good. We were in the meeting, but somehow it froze. And now it looks like that only two people are in the meeting. I don't know. Let's wait, but it says 52 people are connected. So I don't know if the facilitator was froze. Let me see.
You can hear me?
Yeah, I think we had I think maybe Isufu dropped, maybe had an issue with connectivity.
Hello, Teres.
Hi, Lorenzo.
Okay, so I'm reading some messages. Like Adnan mentioned that he cannot hear anything. Can anyone from the community just confirm that you can hear? Yeah, but we need to unmute.
Yeah, through the chat, they confirmed they can hear.
Okay,
I think
yes,
the issue was
yes.
with Isufu.
Yes, okay. So I think we can start so that we keep in time within our schedule. Teres, over to you as a facilitator.
Thank you, Lorenzo. I agree with you. We can go on. I think maybe Isufu, if he refines his connectivity, we will catch up with him. I would like to thank everyone who was able to connect. And yes, we have experts on the call. Lorenzo, I think you will help us to introduce speakers. And you will, so the floor is yours. You can introduce, as I know you are the first speaker, but maybe you can take a round of introductions of our great speakers today before we dive into the actual presentation. The floor is yours.
Okay. Thank you. Thank you very much, Therese. It's an honor, a privilege to be here with so many attendants, experts, and distinguished speakers. So what I would propose is that we go for a self-introduction of the speaker. So let's keep it down to 1-2 minutes maximum each, and then we will proceed with the presentation. So I will start with myself. My name is Lorenzo De Simone. I'm a technical advisor for Geospatial, and I work within the Division of Statistics. I'm supporting national statistics offices in the modernization process with a focus on the use of Earth observation big data for the production of agricultural statistics, hence crop acreage and crop yield. I will leave the word to the floor to Professor Gauzy. Thank you.
Hi, dear Mr. Lorenzo, thank you for your introduction. This is Gao from China, Wuhan University. I'm focusing on remote sensing, especially focusing on onboard real-time remote sensing technologies for disaster response. Okay, maybe I will introduce more in my talk. Thank you.
Thank you. Thank you very much, Gao.
My pleasure. Thank you.
Gilberto, over to you. I think Gilberto wrote in the QA that we need to unmute his microphone, please. I can't find Gilberto in the list here in the participant. Just a second. Gilberto. It seems he's not in the list yet. How is this possible? Okay, while Gilberto connects, I would leave the floor to Eduardo.
Thank you, Lorenzo. Good morning, good afternoon, good evening, depends on you are. I'm Eduardo Vasquez. I'm working at INEGI, that is the National Statistic Office in Mexico, and I'm working in the direction of agricultural and census and surveys. And I'm responsible of the remote sensing projects that are doing at INEGI. Thank you.
Thank you very much, Eduardo. I think, Gilberto, we have enabled your camera and your microphone.
Well, thank you.
Jonas, can you help us?
Hello.
Oh, okay, I can, yeah.
Okay, so good day to everyone. And I'm Gilberto Câmara. I am a former director of Brazil's National Institute for Space Research and a former director of the GEO Secretariat of the Group on Earth Observation. I've been working with mapping land use and land cover and hence mapping agricultural production and area using Earth observation in the later years. And I'll present some of the latest state of the art in the area.
Thank you very much, Gilberto. And finally, Vivian, over to you.
Hello, everyone. So, can you hear me? Okay. So, I don't know if you can hear me well. Okay, great. So my name is Vivian Kerubo, and I'm an Earth observation data scientist at FAO. My role focuses on. Okay, sorry for that. I have to maybe.
She goes now.
Okay. Apologies for that. So, as I was saying, my name is Vivian Onyeki, I'm an Earth observation data scientist working at FAO in the Office of the Chief Statistician Division. My main role aims on supporting of development of tools for crop monitoring and land cover monitoring using machine learning and Earth observation. Thank you.
Thank you very much. So I will go on to move on with my presentation. Please feel free to write down your questions. By the end of the presentation, we will have 5 to 10 minutes of questions, and these will be also the same for the other presenters. Okay, let me share my screen. Share screen, okay. Okay. Just a second. Okay, so I'd like to go through with you regarding 4 or 5 main topics. So the relevance of Earth observation data for land cover land use statistics, just as a refresher, especially for our colleagues, statisticians. A brief review of the current work of the UN task team on Earth observation for agricultural statistics. So understand how it was established, what is the scope of the work. Then provide some highlights on the criticalities when it comes to use Earth observation data to work with crop acreage and crop yield. Present on some solutions developed by FAO within the EOSTAT project since the last 4 years, and provide some highlights on the new work plan of the UN task team. So as we know from the, let's say, institutional point of view, Earth observation data have been recognized as an instrumental data source for the modernization of national statistics offices and also for the reporting to the SDG framework. This has been recognized by the UN General Assembly resolution. It has been recalled by the main geospatial international working groups such as the GEO, the Group on Earth Observation, but also the UNGGIM. Earth observation data are seen both as complementary or either as an alternative to traditional field-based statistics. And of course, the advantages coming from Earth observation are their large geographic scope, high spatial resolution, high frequency of updates, and they come for free or at relative low cost. Furthermore, geospatial data have been defined among, let's say, essential layers of information for countries to achieve their SDG objectives. And in particular, land cover and land use, they have been identified among the list of fundamental geospatial layers by the UNGGIM. As we know, land cover informs us about developing land management policy, understanding spatial pattern of biodiversity, predicting effects of climate change. It can also help to forecast other phenomena such as erosion, flooding, and so on. Furthermore, the land use instead informs us about the land management carried out by anthropic activity, the impacts, especially on changes in natural resources, agriculture, and so on. Furthermore, as the land cover land use data can also be used to monitor and report on SDG targets through the SDG indicators. Some of these have quite a good geospatial footprint. In particularly in this slide, you can see how land cover change, land use, land ownership, they fall under specific SDG for the scope of reporting. So land cover and land use data, how they support SDG and how do they support statistics? Well, essentially, in a country where a solution is in place for operational production of land cover maps at the national level with a stable quality over time, so using a standardized approach, then of course we can extract directly from those maps land cover statistics. We can assess land cover trends. We can assess land cover change and hence land cover change statistics, but we can also extract SDG indicators which are based on land cover data, such as the case of the 15.4.2, the mountain green cover index, for instance. If we look at crop maps, so crop map is really a specialization of the agricultural land cover class. So it is really a land use map because it informs on how the crop land is being used, which type of crops are being produced. And of course, the capacity of using Earth observation data to produce an accurate national-wide crop type map opens the door to many applications. So early estimates of crop statistics which can be disaggregated at subnational level, so at province, at district, down to the plot level. And then when coupled with the crop modeling, we can use the crop type maps for crop yield forecasting. And then we have also early warning, disaster impact assessment, and market analysis, as we will see in the slide, in the next slide. Yes, this is let's say the typical workflow. So if we have a land cover map established in a given country, then we look into the agricultural land, then we can further specialize that class. We can, for instance, detect field boundaries, and then we can discriminate between the crop types. And of course, when we couple this with crop yield, then within the plots, we can detect the crop yield and the differential crop yield, with which then we can extract crop yield statistics. And then finally, combining these with flood monitoring, for instance, or with drought monitoring, it really allows us to see how the disasters have impacted the cultivated areas. And this has, of course, an impact on the final agricultural statistics. So in a nutshell, we have different, let's say, type of applications that can be built on top of crop type maps, field boundary maps, crop yield maps, and flood and drought maps. Few words on what is the UN task team on Earth observation for agricultural statistics. So a task team on Earth observation for agricultural statistics was first created in 2014 under the Global Working Group on Big Data for Official Statistics, which was established under the UN Committee of Experts on Big Data, the UNCBD. In 2021, the team merged with the task team on Earth observation for agricultural statistics, established by the Committee of Experts on Food Security, Agriculture and Rural Statistics, the UNCIAG. So the focus of this group is really to develop use cases to demonstrate the use of Earth observation data for official statistics, the development of methods for the use of optical and radar data for crop statistics, and in time, the team has collected those use cases and has produced official reports. So we have a report from 2017, another one in 2022, and another one has just been produced. What's relevant to say is that the task team is composed of 3 subtask teams. So we have a team working on methods, another one on data sharing, and another one on training. And the participation to the task team is by UN Big Data regional hubs, NSOs from countries globally, UN agencies, UN Big Data regional hubs, sorry for the repetition, development funding bodies, Earth observation big data providers, international Earth observation working groups, and of course, as of the join between the 2 committees, of course, the participation has further expanded. It's worth noting that FAO is co-chairing the task team together with the INEGI and with the World Bank. This is a nice picture that was taken in Hangzhou in last November, as the UN Global Big Data Hub has been established in China. So it has a transition from a regional hub to a global hub, and a dedicated remote sensing laboratory has been established. This, of course, opens the door to new collaborations and interesting new venues for geospatial. So what are then the key challenges? What's so complicated in crop mapping and crop yield mapping even more? So here I'm just sharing with you a typical workflow, and it is, of course, a theoretical one. There are many ways to go about this, but in theory, when we work with crop type mapping, we have to identify our area of interest. We have to identify the agroecological zones within which we want to work. Secondly, So the crop calendar, of course, that's a fundamental information. Secondly, we have to work with the satellite data that doesn't come in a ready-to-be-used format. So we need to pre-process the images. So we need to go from scattered information to harmonized and standardized time series. And there's going to be a lot of talking about this, especially Gilberto is going to illustrate a lot of this. So the pre-processing then also involves the art of interpolating values for pixels when we have clouds, but also at time interval when there is no acquisition. And then from all of these, we're going to extract the features. But where do we extract features? We extract features in correspondence of the so-called in situ data, which is our ground truth data. And this is another issue that is associated to this because of the lack of in situ data, as we will see in the later slides. Finally, then we apply a classifier. It can be a random forest classifier, so it's a decision tree approach, or we can use a pattern recognition algorithms like the dynamic time warping, etc. And finally, we have to validate the results. And again, also in validation, there are many issues because, as Gilberto will also provide more insights, one thing is to validate the fitness of a model, but another thing is to validate the quality of a map. So the issue with crop type mapping, I will try to go a bit faster in order to keep up in time. So essentially, in situ data, georeference crop data of high quality, of adequate quality is scarce in countries. Often data is georeferenced in an inappropriate way through field surveys. So as you can see in the images on the top, the field enumerators have gathered GPS points along the track, and they are not instead just focusing on the parcels. In the below image on the right, a single GPS point is collected at the intersection of 4 plots. So it's difficult to know which plot is represented by that plot. On the left here, instead, we have 2 centroids, which are okay. Another issue is that often the georeferencing takes place at the household during the agricultural survey and not at the plot level, and this is another problem. So in essence, it's very difficult to go from available in situ data to this type of images that you're looking at right now, where you have the nice polygons around the parcels. This takes a lot of time and a lot of money. Furthermore, usually agricultural surveys conducted in the field, they overestimate the major classes and they underestimate the lower classes, and this creates a problem of confusion in our classifier. So we have contamination of major classes into minor classes. Currently, the methods for mapping croplands are still very much data hungry. So you can see the guidelines from the JCAM, for instance, where they advise that for a cropland map, we would need around 1 observation every 5 square kilometers, or for a crop type map, we would need at least 1 observation every square kilometer. So this is a lot of data essentially that it requires. Science is not yet there in transfer learning, in the sense that somebody may say, okay, if I have a in situ data for one country, can I use this to predict in a different country, or can I use this to predict in a different year? Unfortunately, transfer learning is still showing some limitations in doing this. And finally, we have problems with cloud coverage. So countries where we have a lot of cloudy days, then we need to use radar data, which introduces more noise and it introduces new complexities. Regarding the crop yield forecasting, the crop in situ data for crop yield is still quite suffering from the lack of standardized protocols for harmonized data collection. And furthermore, yield forecasts based on a limited number of crop cutting remains highly uncertain due to the large spatial variability of the crop yield. So how is FAO trying to respond to those different challenges? I'm going to show some examples from country projects. Very briefly, EOSTAT, which stands for Earth Observation for Agricultural Statistics, was launched in 2019 as a geospatial branch of FAO's Data Lab. It started with a couple of countries in 2019. Now we are working with 21 countries globally. Essentially, what we do, we establish a project team with nominated experts in NSOs or line ministries concerned with agricultural statistics. We discuss together to understand the expectations from the country stakeholders on Earth observations. Then we review the methods in the country for data collection, and eventually we suggest recommendation to adjust the field survey data collection so that it is fit for Earth observation work. We identify jointly the requirements, and then we co-design solutions of tools, for instance, which allow for automation of routines. As Viviane will show in the last presentation of today's webinar, you will see a hands-on exercise using a tool that automates a lot of those processes. And of course, we deliver training, so workshops, on-the-job training, and webinars. Some use cases from the country. So I still have 7 minutes. So in Zimbabwe, we've been working under the Zimbabwe Emergency Food Production Project, funded by the African Development Bank, in collaboration with the Ministry of Agriculture, the Statistical Office of Zimbabwe, and the Zimbabwe Space Agency. We started with the first objective to map winter wheat for the winter 2023. So because of the lack of in-situ data, we had to deploy an ad hoc field survey. We worked with enumerators from the Agritechs. We used the ESRI Survey 123 app to collect the data. So we gathered 619 ground truth data. And then for each location, of course, we took note of the type of day, of the type of crop, if it's irrigated or not. We also asked the farmer of the previous yield. And we used then Earth observation data to extract for each point the pattern, the NDVI pattern. So we used that pattern to train a random forest. And finally, we developed the first winter wheat national map for 2023. I will spare the details on the processing, but of course we can go into that if you have any questions. When we validated this map using part of the data that was gathered, the model scored an overall accuracy of 86%, which is certainly above what we would get from the World Serial local accuracy for the country. Of course, the map needs further inspection, so we just produced this map in November, essentially. Some examples of the map. So you can see how the winter wheat is nicely depicted in yellow, and in pink you have the fallow, essentially, and in gray you have the no crop. We also delivered a web GIS application, so if you're interested in inspecting the map in a dynamic way. This slide shows our effort then to use that methodology and package it into an automated tool. So on the top, you can see the codes from Google Earth Engine, but below you can see the interface of the crop mapper, which essentially then can be used without going into the codes anymore. For Senegal, we started the collaboration in 2019, and we worked with the DAPSA and the Office of National Statistics. And for the first time in 2019, we managed to produce a national crop mask using Sentinel-2 data and random forest with a rather high accuracy, as you can see. And from that map, then we could differentiate the crop types, so the main crop types and the minor crop types, and from these to extract the crop average. But of course, initially the results weren't so good, so we only had 78% of accuracy. Then what we did, together with the country, we decided in 2021 to have a pilot survey where we would use a specific design which would enhance the georeferencing of the crop parcels. And finally, we could show that when we used good in situ data, then we would have an overall accuracy of 90% for a crop type map. So based on this, we could derive recommendations to the Ministry of Agriculture in Senegal for the future annual agricultural statistics. And essentially, we recommended that the plots should be georeferenced, so the borders, but also GPS should be collected in the centroid, and the same should be done for the crop cuts. And as a result of this, those recommendations have been endorsed by the DAPSA, and now they're implemented de facto within the annual agricultural survey for Senegal. So in this way now, the country is going to produce on a seasonal base in situ data which is fit for purpose for crop type mapping. We also could show that when we use in combination Earth observation data with good in situ data, then we have an increase in the accuracy of the estimation. So we reduce essentially the standard error of estimator of proportions, so of the area of the acreage. So you can see, for instance, for millet and groundnut, when we only use field data, we have 3.3 of standard error. in the average estimation. But when we combine instead field and satellite data together, we basically decrease the error almost by 50% essentially. And this shows an efficiency in the use of satellite data because, of course, satellite data is for free, Sentinel data is for free. If we wanted to achieve the same enhancement using traditional methods, we should intensify the sampling, which would come with a lot of with high costs. We also tried crop yield, so to correlate crop cuts with Earth observation data, specifically the land leaf area index, but unfortunately we couldn't really establish stronger correlations. And then checking with the experts, we realized that there was a problem in the georeferencing. So we are going to repeat the exercise this year. In Mali, similarly, like for Senegal, we're working with national statistics in order to improve, let's say, the field survey design. So we are using Earth observation data to drive a dynamic stratification. And we're using the European Space Agency World Cover Land Cover Map to create strata of agricultural intensity. And then within each strata, we're going to randomly select segments, 500 meters times 600 meters. And then within each segment, we're going to digitize crop of parcels using Google Earth Engine. And then those digitized parcels are going to be available to the enumerator within the tablet. So we're changing really the business model here also for the protocol in the field to make it easier. In Lesotho, the collaboration was established with the Bureau of Statistics, and we managed to deploy an operational land cover monitoring system, which uses Sentinel-2 data random forest, which is able to produce in automatic way annual land cover maps, and from this to extract the statistics, as we saw in the previous slide. What's worth mentioning here is that the method is standardized, so this can be used essentially to compare maps across times. We have a methodology which can be used also to other countries. Finally, this project was awarded with the GeoSDG award prize in 2023 for the integration of geospatial data with statistical data. Finally, Rwanda, we're almost done. We are piggybacking from the experience in Lesotho. So we are implementing a new methodology which modernized the old methodology for the land cover. So what we did, we delivered the first prototype without any training data, without in situ data, and we had an overall accuracy of 76%, which is still low. But of course, we didn't use any in situ data for this. And just let me show these last two slides and then I will stop. Essentially, we moved from a monotemporal approach based on visual interpretation to a time series analysis approach. So the 2015 map, which you see here, is based on visual interpretation of a single image acquisition. And you can see that in this area, the satellite image on the left shows that you have some forest, you have some urban, actually rural settlements, you have some roads, you have some forest and some water also. But on the right-hand side, essentially, the map is telling you that you have mainly agriculture and then you have moderate sparse forest. When we instead use time series analysis and Sentinel-2 data, then you can see that the map is much more rich in detail. So this to show the advantage of working with time series data. I'm out of my time, so I will stop here so that I respect the time for others. And we have now from 5 to 10 minutes for questions. Thank you.
So thank you. This is very interesting. So are there questions from participants? I'm not sure that I can see whose hand is up. Okay, I see one hand. It's Mr. Odinao Adeni. Mr. Odinayo. I hope I'm pronouncing correctly. Otherwise, there's also Mamadou Ndia. The floor is yours. Are the participants muted?
Gao, I think you raised your hand as well. You're muted.
Okay, can you hear me?
Yes.
Okay, maybe I have one question about the transfer learning part. Now, as you said, you try to using the transfer learning technology to predict the yield of other country or other places, but the results may be not good enough. So my question is, what did you guess? What kind of problem it is for the reason of the data you captured already, or for the model not good enough, or the training strategy, or any other issues? Thank you.
Thank you very much, Gao. Yes, the question refers to a composition of challenges. First of all, the quality of the in situ data, clearly. The definition of good stratification, because if we are good, generally we work with agroecological zones. Now, agroecological zones have been defined in the past in quite, let's say, a coarse way, I would say. Instead, for crops, we really need finer microclimate conditions in order to ensure that you have homogeneity. So the problem is, how far can we expand? Do we have any insights? So if we look at, for instance, the Google dynamic layer, dynamic cover, now they have those bands of probabilities, which are much finer grained. So I'm thinking that probably we should look at a better use of dense time series to allow us to identify homogeneity. And this can definitely allow us to increase our capacity to transfer the learning, first thing. The second thing is also, as a starting basis, we don't really have time series of in situ data from countries, because in order to train also machine learning or artificial intelligence, a gradient boost, for instance, I don't think it's sufficient to have just some scattered data for 1 or 2 seasons. We need consistent data for 4 or 5 years together with the remote sensing data. And then I think there is enough intelligence to be able to predict. So we are still starting, and I think that the work that FAO is doing with the NSOs to make sure that when they gather data through the established field data mechanisms in the country, that they are suitable, then that will generate that database, that foundation information, which will allow for that training, given that appropriate time series work is done, of course. Thanks.
Thanks for your answer. Thank you so much.
Mr. Adenir, can you hear me? Your hand is up. Otherwise, Mamadou Ndia.
Yes. Hello, everyone. Can I speak? Do you hear me?
Yes. We can hear you.
I'm a new engineer in DAPSA, and I hear the Simon speak like he collaborates with DAPSA. So I'm new in DAPSA, and I work on modelization. And I would like to know your intervention with the statistical agriculture for DAPSA. If your collaboration, you build tools to predict crops, or what? I would like to know well what you do with DAPSA, and also if I can collaborate with you and see what you do, so collaborate with you to build tools, our tools to predict crops in taking account precipitation and soil property.
Thank you very much. Thank you very much. So I will briefly explain the collaboration with DAPSA. So we started in 2019, and a focal point was nominated in DAPSA, which is Madame Sylvie da Silva. So she's the head of the survey team, as you know. And essentially, what we did at the beginning, we used the out-of-the-box tool, which is sent to Agri, ingest the data coming from the annual agricultural survey from 2019 to produce the first crop mask and crop type map. And then we sat together with Sylvie, but also with the ANSD and also the Suivi d'Ecologie, the other center you have in Senegal, just to understand which were the limitations. Then we've been working with the team of DAPSA on survey to review the survey protocol. And we did this exercise in Nioro. And then we formulated those recommendations which were endorsed. Now, the last step that we would like to do is really to work with DAPSA in 2024. One, to update the national map for baseline 2024. Second, to automatize the processes. So we are using Send4Stat, but we are also using now Google Earth Engine and Digital Earth Africa. So the idea is to experiment a solution that is easy to replicate and doesn't need coding. So we're trying to understand this. And then the last topic is crop yield. Now, we had a crop cut session in Nioro, but as explained, there was a problem in georeferencing. So in 2024, ideally, if we could gather a good crop cut sample, then we can use three types of crop yield models. We can use a statistical-based model, which is inbuilt in Send4Stat toolbox. And then we can use two physical-based crop yield models. One is the SALUS, developed by Michigan State University, and the other one is the DSS-SAT. So this is the plan that we have for 2024, and I would be very happy, if you get in touch with me via email, and we can then see how to bring you on board of the project. Thank you.
Okay, we have Mr. Birara Gebehu. Maybe two more questions just to stay on time.
Hello, can you hear me?
Who is it? Yes, we can hear you.
I'm speaking.
Yes,
oh,
yeah.
Thank you. Okay, I just want to ask a quick question. I'm an African research fellow at the European Space Agency, and actually working on using Earth observation to monitor soil moisture content and see how it affects crop productivity in Nigeria. However, I'm just curious to know, aside Google Earth Engine, what's are you also using any other cloud computing interface to compute this large big data? Because I could see that you work with 10-meter resolution of land cover, and that's a huge data for an entire country. And the second thing is that, of course, in a place where there are limited institute data, is it possible to, I don't know about your experience with semi-supervised learning and some unsupervised learning methodology. Can this methodology or technique really work in such a case? And do you have any experience about that, and how does it work?
Thank you very much, Mr. Odunayo. So the first question, if I'm not wrong, if I understand well, is about soil moisture and using this data from Google Earth Engine. So yes, we use potential evapotranspiration and actual evapotranspiration to indirectly assess soil moisture. So we've been working with that in order to assess land productivity potential. But there are many now global data sets available in Google Earth Engine. So I think there are different options there. And then, of course, we can use that in conjunction with global land cover maps in order to isolate the agricultural land if we don't have a dynamic crop mask, if we want to focus on the water availability for crops. This said, regarding the semi-supervised and hybrid solution, so we've been working initially also just with unsupervised, so typically k-means clustering. We tried this initially in Lesotho. And of course, as you know, the k-means clustering is going to group pixels which are similar into the statistical space, and then you will need an expert to say, okay, I think this is the major crops, this is the minor crops. This is subject to a lot of errors, of course. because we don't really know much about that pixel. We need additional information. At the same time, what we've been trying to do, we've been trying to working with dynamic time warping, which is a supervised classifier. Essentially, what we're trying to do, we're trying to define in a specific geographic area a representative phenospectral signature of crops. Okay, and then we're going to essentially use dynamic time warping to assess the similarity of each pixel to a list of reference crop phenospectral signatures. And we let the software assess which is the combination that minimizes dissimilarity. So in this sense, this is a semi-supervised approach because we just create the spectral signatures in one area and in one given year, but then we let the software automatically recognize the pattern. So we go from a data-driven model like random forest to a pattern recognition approach, which is the dynamic time warping. I hope this replies to your question. Thank you.
Thank you. It's clearly a very interesting topic. So the last question from Mr. Birara Yebeyu. We are already behind time. Are you online, Mr. Birara? I don't think he's unmuted. Maybe I can just ask the last question from ACS, just to use my privilege as chair. So we used to have these programs where we want to do agricultural censuses, and then between the censuses we did some small surveys. So here I want to know if this has we can use these methodologies to maybe put more time between two agricultural censuses. This would be in terms of reducing costs, particularly interesting. And then I'm also curious about the possibility of learning from one country to another. I don't know if you have already tried transfer learning, like when you have learned something in Senegal, instead of training everything in Mali, maybe you can use a small sample from Mali and do transfer learning. This would also save cost, but I don't know if it is possible. These are just my two short questions.
Thank you very much. So I have some good news. We're planning in 2024 to test transfer learning because now we have sufficient data from many countries. So we're trying to push the system to see how far can we predict and how can we define this distance in a safe way, because we want to be able to share training data, but also to add the information on how much you can use this, how far you can go with the transfer. So we're going to do this, and we have data for Mali, we have data for Senegal, for Uganda, so we have a series of collaboration. Regarding the World Agricultural Census 2030 is coming up. So FAO is working on the new census. So we are developing a chapter inside the sensors for the use of Earth observation as a support into the design in order to optimize costs, which means reducing time in the field. So we are going to develop a dedicated chapter to that.
This is good news. Thank you.
Thank you. Thank you.
So thank you very much. It was very inspiring. But for the sake of time, we are going to move to the next presentation. It's supposed to be from Professor Gao from One University. Professor Gao,
Hi.
The floor is yours.
Okay, thank you for the introduction. I share my screen.
We don't see it yet.
Yeah, I try to find it. Okay, wait a moment. Can you hear my screen? Can you see my screen?
Yes, now it's visible, but not full screen.
Okay, can you see my screen? It's
yes,
full screen
it's okay.
Now. Okay, Thank you, everyone. Thank you so much for the introduction and the invitation to give me such a chance to present my work in my team. Actually, this is an ongoing project here. The topic present in the homepage is your use of EOSTAT for integrated monitoring of agricultural resource and disaster impacts. Actually, in my team, the ongoing project is called a GNN, Graph Neural Network based Earth Surface Anomalies Detection Framework. I'm Professor Gao Zhi. Gao is my surname, Zhi is my given name. Actually, this work is from Wuhan University and my students in NUS, National University of Singapore. Okay, this is the outline of my presentation. Firstly, about me. Actually, it's about Wuhan University. It's located in the central part of China. Actually, it's among one of the top-ranked universities, maybe top 10 in China. Actually, our campus is very famous for its beautiful. So I welcome every one of you guys to visit my university. Actually, the school is called Remote Sensing and Information Engineering. Actually, we are strong. Actually, in many ranking, we are in one of the top ranking of the remote sensing technologies. This is our major. Okay, actually, this is about myself. Actually, I'm a professor and a deputy dean of the school. So I'm keen, not only myself, but also my organization and my colleague do lots of remote sensing research, especially for some artificial intelligence, AI, and remote sensing image interpretation for this part. This is the background and the motivation of my work, my research. I think everyone knows that the disaster, not only caused by the natural side, also from some human-made side, so that the disaster brings us lots of dangerous and lots of problem and give us heavy impact of our safety and lots of issues. So, of course, remote sensing is definitely one of the key technologies to monitoring and to give the necessary information for faster response. However, this is say using remote sensing technologies, segmentation and detection and segmentation can give us the information of how serious before and after the earthquake it affected. However, the current working mode of the remote sensing technologies is that the satellite captures data and then transfer the data to the ground receiving station after processing and then send the information to the user. So only the data can be transferred to the ground for processing within a limited time window and leading to long response time. So most of the current remote sensing technologies are post-event analysis. So the time delay, so the time issue, the efficiency issue is a big issue, is a big problem for the current remote sensing technologies. Of course, based on the current analysis, we're using multimodal, multi-temporal data for comparison to find what happens and the size, the scale information. Actually, in our case, we design another kind of working mode of the remote sensing technologies. It means we can do the AI intelligent interpretation, intelligent processing of the image data on board. It means in orbit anomaly detection and then passing the results to the user. It means it is no longer, we no need to send the data to the ground station for processing. We do processing on the satellite and then to pass the necessary and the essential, basic, and the most important information means where, what happens, and the scale information to the user. Of course, here we can say that to reduce the detection time and also to save valid time for response, we design such kind of strategy. Firstly, we use simple data instead of multi-temporal data. For example, instead of using comparison, multi-temporal comparison methods, we only use single satellite image to do such kind of anomaly analysis. And then we apply the lightweight and a tailored model for the processing. This is our basic strategy. First one, simple data and more smart and a light-weighted model for the processing, onboard processing. Okay. Actually, we use graph neural network to realize, because we try to simulate the process of human brain to interpret the satellite images, what happens and where, and the scale and the size. Okay. Firstly, why our methods works, we must clarify a little bit the function, the powerful points of the graph network. For example, graph representation through nodal representation and topological construction. Usually, it has been publicly and popularly applied for 4 kinds of tasks. For example, is graph classification. It means the overall classification. And the second is node classification. It means different components, different parts in the image. We call it the node. We can also do node classification and the link prediction. It means we can predict the relationship between the nodes. And the fourth is the community detection. It means within the graph, there is several regions, several parts. Using our graph theory algorithm, we can realize such kind of 4 main tasks. And our methods are mostly based on such kind of 4 kinds of pillars. Okay, actually, inspired by the AR-based synergistic approach, it means the doctor, for example, the doctor just sees the image, maybe a CT, maybe a PET image, and then to do the analysis. Of course, use the doctor's brain, use its knowledge, experience to do the analysis and make the conclusion. Of course, our remote sensing images, also single image interpretation, also follows similar processing flow. For example, the single satellite image, we extract the content and the features, and then generate the graph representation and to do model training and inference. And then after this, we do the Earth surface anomalies discovery. And then for vectorization, it means vectorized representation to give statistic information. This is our general overall data processing flow. Okay, this is motivation is that what happens and where happens, and the vectorized representation, it means the scale, the size. Okay, about our methods, maybe I think it can be roughly divided into 2 important parts: the graph generation and anomaly detection. The second part is anomaly segmentation and representation. Okay, first step is a hierarchical geometry to semantic fusion, a GNN framework. It's called GNN. I highlight again is graph neural network. First part is to generate the graph. It means from the single remote sensing image, we should obtain the graph representation, right? Based on the, so firstly, we're using the low-level geo entity. It means using some superpixel segmentation, and then we can generate the low-level graph based on the similarity between pixels, superpixels, okay? And then we using some straightforward methods to generate the node and their central points, and also the node vector description. And this is to construct the low-order graph topology. Second part, we should use some a little bit high-level information. It means we're using some object and semantic information to generate our high-level graph. For example, we're using some pre-trained semantic segmentation model, and then to generate a feature map, and then we generate we obtain the segmentation results. And based on this one, we should do the externalization. It means although they are the same parts, the same semantic regions, for example, the water body in the forest, but they are separate, independent. So we give them different ID, different node. So we generate the high-level graph. Definitely based on between the low-level graph and the high-level graph, we know their geometrical relationship. So we can generate the assignment matrix, okay? Based on this one, we can use this one to generate the topology relationship. And then after the graph generation part, we can combine them together. For example, the joint will include the low-level, high-level, and the assignment matrix from low to high, their relationship. Based on this one, we can realize Earth surface anomaly detection. Here, I should emphasize is that here we just say anomaly detection. We do not know what kind of anomaly it is, but we can realize anomaly detection. For example, based on the low-level graph and the high-level graph, and then we're using the assignment matrix to combine them together to generate the hierarchical GAT. It means graph attention network. Based on this kind of combination, we can combine the low-level and high-level information for our high intelligent anomaly detections based on this one, okay? So here is an MLP, multi-level perception, based on the convolution processing and the MLP processing. Actually, based on this one, we definitely need to design some parameters and functions for in our network. Based on this one, this is some operation. I will not go into the details, but I should say it works and very effectively. It can help us to do the detection, anomaly detection. Based on the detection, however, it's not good enough. We need to do anomaly segmentation and representation. It means we can design this, for example, for this satellite image, something happens, but we do not know where the anomaly happens. So we need to do anomaly segmentation and also to decide the size. But we have so many problems because the main problem is firstly is the limited annotation, because the pixel level labeling is time consuming and non-trivial. For example, everyone knows that if we want to do the pixel level segmentation, we need the pixel level labeling if we apply the supervised methods. So second, is that the semantic complexity, because the intra-class diversity and the interclass similarity scales. For example, in this one, this domain gap in the remote sensing image, intra-class diversity, interclass similarity, basketball court and a tennis court. They're different, but they're quite similar, right? And then all these are church, they are the same, belongs to the same semantic, but their appearance are very different. For example, this is the domain gap issues. So based on the three challenges, we can use, what we can use is only the weakly supervised labels, because just as I mentioned before, these images, for example, previous, if you remember, we can label it as normal or abnormal. For example, if this one we already decided it classified it as an anomaly one. So this is the label. So we just use the weekly label to do the further processing. This is the inexact label, where the training data are given with only coarse-grained labels, and an incomplete label, only a subset of training data is given with labels, and noisy label, where the given labels are not always ground truth. All this information actually is exactly what our previous step, the anomaly detection, can provide, just a single label. And based on this one, then we can do the anomaly segmentation part. Okay, actually based on this one, this is our already, this is a label, anomaly flood. This is our prediction. This is the original input image, and this one is a simple pixel one. So based on our previous framework, we can, if you can remember, our local graph and a high-level graph, and then the relationship, we can recalculate the accessing the impact level and generate a pixel level attribute to the image for further analysis. It means if this image is defined as anomaly flooded one, what kind of nodes contribute most to this kind of conclusion? Then based on this one, we can get the node prediction. You see, based on this one, we can combine the node information and the super pixel information. We can get to the attribute image. It means where the pixels belongs to. A normal contribute to the abnormal conclusion, or do not contribute the abnormal conclusion. Based on this analysis, we can do the vectorization, and vectorization means the statistical information, the size, the scale, the area. Okay, we just see some experiments part. This one is our, we generate the EOSTAT, it means the Earth surface anomaly detection dataset. It includes more than 13,000 samples, more than 11 class very popular disaster images. So we based on this one, we can, this is our anomaly data and the normal data for this statistical information of our data set. And based on this one, we can do we can check our classification results. If you can see that, actually our results is here, it's much higher than the previously graph-based one. And here, the VIT one is Fourier transformer methods. Then you can say that the overall and the recall is higher than us, but the size, it means the parameters and the processing hardware requirements is much higher than ours. And this is our processing time and the parameter, the network size. Actually, this is our methods. And then this is a vectorization, a vectorized representation. And you can see that we can provide the regions of anomaly pixels. It means we can provide the statistic information about the pixel numbers and the areas and the regions of the disaster happens. Then conclusion, actually we try to improve our model performance. It means to improve the overall model precision recall. So actually we are trying to using better training strategy and such as include more data, because currently we just introduced the framework. We can include more information in the framework for higher performance. Secondly, we are trying to construct the dataset with larger sample size and more comprehensive types of the surface anomalies. Secondly, because in our university and our partner, we have several satellites. We try to configure and deploy our algorithm on the satellite for immediate onboard detection and diagnosis of surface anomalies of the downlinking of and then downlinking the results. Thank you for this chance again. This is my WeChat. If you use, you can definitely scan the QR code, and this one I can be reached. And this is my email. If you have any further questions, of course we can discuss now. But if you have further questions, please send me the email. And also I seek any further cooperation. Thank you so much.
Thank you, Professor Gao, for this inspiring presentation that show the power of machine learning applied to satellite image. So are there questions from the online?
If I may, there is a question in the chat from Eche. Thanks for the presentation. Have you ever applied the model in different regions, countries? Is there any automatized monitoring system?
Yes, this is a very valuable and good questions. Currently, we only tried the disaster models or the types of disaster only in the China region, within the China, because China is already have so many natural disasters. So we do not have tried any other countries yet, but some very popular and often seen disaster, we definitely can intelligent interpret, such as flood, fire, and earthquake, etc. I hope can contribute for some project in Africa.
Okay, thank you. So
thank you very
questions?
much, Gao. If I may just chip in, Eche, the colleague who asked the question, she works in the Office of Emergency in FAO. So clearly your work is very relevant to her business. Thanks.
Okay, thank you. Actually, our methods, I mean, I need to highlight, emphasize that definitely for you will get more accurate, more precise results. Definitely, you will have more data, more information sent to the ground for some super machine processing, definitely to provide better results. But our methods is fast on board, can send you some alarm or quick information. Definitely the accuracy somehow is compromised. But the key point is the timing, as soon as possible.
Okay, thank you. I have two questions. just from statistical viewpoints, can you use these anomalies that you detect in forecasting or in nowcasting? I imagine that for agriculture, maybe if there is a big anomaly, it's an interesting information that we can put in your nowcasting model, and it is useful for policy. And then my second question is, you are using satellite image, and I don't think many African countries has access to the satellite imagery. It's very expensive when we are trying. So I don't know if the method is applicable also to normal image, or there are some countries who use some drones. So if it could be used for this, it would be very good also for African countries. Over to you.
Okay. Yeah. Firstly, from the statistic viewpoint, right? Actually, definitely in our methods, we not only provide the current time, the size, the scale of the disaster. We want to predict a little bit, for example, maybe 2 hours, 3 hours, or maybe at most 1 day after how the disaster, the scale, the size, for example, the flood, 1 day later, 2 hours later, 4 hours later, more people or more regions was affected by such kind of disaster, right? Definitely, our methods will be extended to provide such kind of prediction, but definitely just as the transfer learning methods, we need to check and confirm, verify the accuracy, the issues. Okay, about the second question about the image, satellite image part, definitely yes. If you are not in supported by any organization to buy the data, buy the image, definitely it's expensive. But in China, actually, some satellite union, you join the for me, for our university, we join the some union. We can share the data. Means, for example, this one university have 2 satellites, and another university has another 1 or 2 satellites. We join together, we share the data. Just maybe this one kind of the strategy or methods to deal with the problem. Maybe we can keep in touch and share some experience in this issue. Thank you.
Okay, thank you very much. So if there are no further questions, we should thank Gao for the presentation, and then we can move to the next presenter, who is Professor Gilberto on Earth observation data cubes and time series analysis for enhanced classification performance. So Professor Gilberto, the floor is yours.
Well, thank you very much. Are you hearing me well?
Yes, we can hear you.
Okay, good. So I'm going to focus on the issues, and I'm trying to complement what Lorenzo and Professor Gao have put on the issues of Earth observation, data analysis in the age of big data. So, of course, I think this is common knowledge that satellite data is now available for everyone. And just a minute. Okay, just a second, please. 1 second. Okay, so now you have a number of satellites available for all of the globe, including very good satellites such as Landsat 8, Sentinel-2, and of course there is in Brazil, the Brazil-China Earth Resources Satellite, CBES. Now, the general trend now with the big data is that the big data needs to be stored and organized in cloud services. And the organization of the data is such that you don't store the data in your local computer, but rather use the organization in the cloud service to perform machine learning. This is not straightforward in general, as Lorenzo pointed out. There is no direct link between the data and cloud services and its availability for machine learning. Normally, there's got to be some pre-processing. But in general, these are 3 complementary trends in big Earth observation data for satellite development. You have the open data, you have the cloud services, and the machine learning methods. One thing that Lorenzo stated, and very well, is that there is, in most cases, need, if you use time, and let me go back to I'll come back to time recently, long in the presentation. You need to organize your data, including a jargon that some of you may be familiar, some of you may not, which is the data cubes. Well, an image collection is what the satellites come out. So is what one sentinel, one after the other, provides you. Whether for example, Landsat 9, 8, 9, 10, whatever. Then to properly use machine learning, you need to organize them in grids of compatible and the same latitude, longitude, and time. And if you organize that, you get the property that if you select a latitude and a longitude, you get a nice time series. So for the same point, calibrated. And if you take one time, you get an image for that time. And one of the issues that has come about as a need in Earth observation for agricultural satellites is that you have the idea of time series. And how did the time series idea come? Because normally many people use each image and classify each image and then compare the results. That's what we call space first, time later. Whereas the idea of using time series is that the time series capture the variation of the satellites in terms of actually not the satellites capture the variation of the agricultural crops. And this is very important because there is change during 1 year in one agricultural year. One nice example is this. This is a dam in Brazil, which was not very well built. And this is like the dam in the end of the rainy season. This is the same area in the start of the rainy season, the end of the dry season. And you can see there's a massive change here. And you need to know this in order to be able to correctly classify this, for example, as an area which was covered by wetlands instead of, for example, covered with bare soil. So you don't want to be limited in your interpretation only by the date you choose. A single date may not capture the variation. And a nice example here is a MODIS time series, where you have for 20 years from 2000 to 2023. And you can see that it nicely shows what has happened to the area. So between 2000 and 2023, this was a forest. You can see this is the NDVI of the area. Nice and high was a forest. And then there is a drop, sudden drop, which corresponds to the deforestation. And then step by step, this area becomes a pattern, which is more or less irregular in time, which correspond to pasture, to planted pasture, herbaceous pasture, which has a nice response, kind of smooth response, responds well to the start of the rainy season. And then the same area has been converted again in 2013. And you can see now signals which are quite different from the pasture signal. And these signals are associated with temporary agriculture. So most of the literature and the experiments point out that using Earth observation for agricultural statistics is very much improved when one has access to the time series. That's why Lorenzo was showing a lot of time series example. The important bit here is that instead of selecting one image per year to do the work, you try to give users all the data, including inter-annual variations, inter-seasonal variations. And that is very important because you can see a nice separation between agriculture, forest, and this is that similar case where you had the deforestation, then the pasture, then agriculture. And the land, the classification of land use and land cover becomes then not a classification of a single image, but you organize the image on a data cube and then classify the time series, because you capture variations of crops which are not present in a single image and are only present if you get the whole time series and the whole season. And so the whole idea is that for satellite image time series, you create a data cube, you introduce that into obtain time series, and out of the work, you select a number of samples, you do the training with the classifier, and then you produce the map. And of course, on top of that, there's another requirement that all of this workflow is captured in open source software, because it becomes reproducible and reusable for countries and not by commercial software. This is an example of patents for Mato Grosso, Brazil, which, as you might know, it's a large agricultural state. So here you see the Cerrado, which is Brazilian savanna, you see the forest, and you see here the EVI, the near middle infrared, the NDVI, and the near infrared. And these are the 4 signals. Here you can see the pasture nicely and smooth, and the difference between, for example, double cropping with soy corn, soy cotton, soy fallow, and soy millet. And this, of course, is information that would not be available if you take a single image or a composite image per year. Lorenzo also talked about some of the classification methods that can be applied. One of them is random forest. So this is an example of the classifiers here for this area taking 2 bands. And you see the explanatory variable, which gives the most power, is NDVI 22. NDVI, we all know, but what is NDVI 1022? NDVI 22 is the 22nd value of the NDVI time series. So in other words, almost in the end of the series. So this means that, in the end, in the end of the series, in the end of the series, there is information. And then you take, EVI in the 17th. 17th is more or less like here. So corresponds to this drop of different drops in the different time series of the different crops, and so on and so forth. So here, what you're actually doing, you're having a spatial temporal classifier, which actually takes into account both the indexes and the value of these indexes at specific points in time. Now, Lorenzo also explained that in many cases, random forest does not produce the best outcome. The best outcome, especially if you have less samples than you don't have 10,000 samples, is produced by pattern matching. And one of the areas, one of the algorithms, which has been quite interesting for pattern matching, is time-weighted dynamic time warping. It's a mouthful for a simple thing. Imagine I have a real series here on black, and I have patterns, which I showed before. These patterns, these patterns of, for example, soy corn. And then you sort of slide the patterns around the image, trying to match. How do they match, best match the time series? So here, for example, you see a pattern of pasture, you see a pattern of forest, you see a pattern of single cropping, and you see a pattern of double cropping. In other words, and you need sometimes to warp time, to do matching, which is not one by one, because you know that some dates, some years, the deforestation pattern, the agricultural patterns are affected by things like climate. So if the peak is a little bit lower, you still want to get it at the start of the season. Agricultural season is a little bit delayed. You still want to obtain it. And so this warping is to adjust the patterns. If they don't, you don't want them to fit exactly the patterns, but the best fit for the shape of that pattern in your time series. Okay, now there are other methods available for time series analysis. So we mentioned random forest, we mentioned dynamic time warping. I'm not going into detail, but there are methods, for example, for convolution neural networks. The idea is here is also simple. You try to convey relations, for example, between two instances of time which are close by, two instances of time which are separated by, for example, 2 months, and two instances of time separated by 6 months. So you want to capture variations. Okay, you have, for example, this trough here, for example, for soy cotton or soy corn. And of course, if a low point here, soy corn, the immediate neighbors should be a little bit higher if the trough is there. But of course, if I'm taking now a 3-month period, I may want to see that this point, which is the trough, relates to the peak here. And their peaks relate to 2 peaks. So if I have 2 peaks, I have double cropping. If I have a single peak, I have a single crop, and so on and so forth. So these methods, all of them work relatively well because, of course, it depends on the number of samples you might have. We have learned that dynamic time warping, it works better, as Lorenzo has some examples, for a smaller number of samples. And for a larger number of samples, sometimes the deep learning methods work better. Now, this is one example in Brazil, which uses Landsat for the Cerrado area and has a land use map. There were a lot of samples, 48,000, using convolution neural networks with the Landsat 16-day time series. So we saw 8 petabytes processed in 24 hours. Now, the important thing here is that what you want, and you want that if you do your agricultural mapping in Zimbabwe, in Senegal, in your country, why do you still do it if there is obviously information coming from global maps like World Series and similar? Well, the problem here is that sometimes those that are the producers of the global information do not and are not able to capture variations. For example, in this case, I'm going to show you an example of a variation between a natural landscape, which is the Cerrado, and a human-derived landscape, which is the pasture. So let me show you one example. This is on the top, ESA World Cover 2020. And the green areas are areas of forests. And in the sort of pink areas are cropland. But then there is sort of a yellowish tone covering the full image. And this is what World Covers calls grasslands. But in fact, when you do a proper classification, you actually have to distinguish the natural savanna and the pasture, which World Cover does not. And here with the temporal convolution neural network classifier, with the time series classifier, this was a single decision tree classifier in one image per year. Because of course they had limitations of processing. And then you can see here the green places, green places are places where you have the Cerrado, which is natural vegetation, and the so-called sort of yellowish, very light yellow pasture. So you can see one side of the river, there's a lot of pasture. In the other side of the river, there is a lot of natural vegetation. And this information is not conveyed by the World Cover map. So it's very typical that what you produce in the local map with time series is much better than what is produced by a single image in global maps. This is now the latest example. on classification. This is done by the Brazilian Agricultural Agency. And basically, this is Sentinel-2, 10 bands, 10-meter resolution, 16-day time series, TEMP CNN method. And the accuracy was more than 91% uses accuracy for the core class. This is not the overall accuracy. The critical classes had more than 91 user accuracy. And this is very detailed information. It becomes the Brazilian national information. This is the official map for Brazil. And of course, there is a reason that we want to be accurate. The reason, as many of those in Africa know, one of the reasons is the new regulations, such as the European Union deforestation-free goods. You want to prove that the crops that you are exporting come from areas which are free of deforestation. In this case, you need to be better than 90% or even more. So accuracy is necessary, because what you want is not accuracy. You want compliance. You want to be sure that that producer in that area is actually able to comply with the necessary export regulations. One other point that a single image cannot capture, it's very interesting. This is, again, back to the world maps. This is more deforestation, but look at the Sentinel data for 1 year. Then this is the visual classification that is done by Brazil INPE for 2021. And this is the official map for Global Forest Watch. Now, when you look at the image on the left, what you see is clearly there are areas which are being deforested. And the areas marked within that ellipse are not actually land change classes by humans, but are natural areas where there is wetlands and there is a pulse. And so when the human interpreters interpret this, they do not consider this as something that is deforestation. No forest has been removed. But then when you go to Global Forest Watch and GLAD, you see that a lot of the areas are flagged as removed forest, which is not the case. And this is the reason, not because GLAD is bad per se, because it only uses one image per year and therefore does not capture the pulse, the temporal pulse. And when you actually compared time series analysis with visual interpretation, you get a 95% accuracy. So what is that we want to have? What we want to have is solutions that work for different producers such as Digital Earth Africa, Amazon, Microsoft Planetary Computing, CPAL, in our case, Brazil DataCube, in software, which is open source and accessible and captures the satellite image time series information. And this is, I think, one of the most critical advances we need to have in the areas of deforestation, is that you want to have such advances that allow, not deforestation, land use change, that the advances that allow the countries to actually, where is it? Stop sharing. Okay, I'm sorry. So what you want is then to have the tools to allow and to enable image time series information to be accessible and processed by the countries and agriculture statistics for whatever they need. So I would complement my work with Professor Gao and certainly with Lorenzo, that one of the areas that we would like, FAO would like to support the countries is improving their ability to extract information from time series. With that, I thank you very much.
Thank you, Professor Gilberto. So are there questions? I don't see anything in the chat. I see Therese.
Thank you, Professor Gilberto. My question maybe is more general. I wanted to ask, maybe you can add to it, or Lorenzo. Yeah, we now can understand somehow the benefits of using satellite images time series to get a bigger perspective of what is happening. But now, as you might have maybe realized, some countries are not allowed to use cloud services. So what is the guidance in that way? How are you tackling the issue? Over.
Okay. My question here, just back to you first. Are you allowed to use Digital West Africa or not even Digital West Africa?
For instance, now I'm speaking as a user now. From Rwanda, we even have discussions with Digital Earth Africa, but at the moment we are not. For instance, if we are to share national data in situ data, we are not allowed to give to the cloud.
No, but okay, let me give you 2 points.
Mm-hmm.
Okay, let's start with the easy ones first. Countries like Rwanda, up to middle-sized countries in Africa, can actually build data cubes in small machines and laptops, because what you're talking about is sizes which are reasonably small. When I say reasonably small, it's anything less than a terabyte. That's what I have in my MacBook. Okay, so let me start with saying less than a terabyte covers your country. In that case, basically what you do, you access Digital West Africa or Microsoft Planetary Computing or Amazon for free. And you download the data from there for the tiles, for the regions that you want, in the case Rwanda, for the period that you need. And after that, it sits on your machine and it's in your country. You don't have to ask permissions to anyone. This is simple and works for middle-sized countries. For countries which are not so small in Africa, I would strongly try to recommend Digital West Africa, because I still think that's a communitary solution, which there's a lot of support, there's a lot of work there. But if you can't, I always say, okay, if you really can't, it's a piece of cake in terms of software to download the images from these providers, and you don't have to pay anything to do that. Anything. There's no cost involved in obtaining Sentinel-2 images for Rwanda or Sentinel-1 images or both to a local machine. It's just sometimes for big countries may not, like, for example, Angola, RDC, may not be feasible. But for mid-sized countries, I don't think there's a major problem.
Okay, we have a question from Lorenzo.
Thank you very much. I wanted to chip in to Teresa's question, but also then have a question for Gilberto. So for Teresa, as you know, Teresa, when we discussed last time in Kigali, essentially we can definitely work on a server deployed solution. So we can go for Send4Stat to demonstrate how we can download satellite images, build the data cube, and use a supervised classifier. So that's in the plan. But then the question would be, the question is, what do we see in the future in terms of sustainability of the solution? So let's imagine that we can actually build our own cloud solution in Rwanda. So it will be a Rwanda managed data cube. Maybe collaboration with the Rwanda Space Agency can provide sustainability. So my question then for Gilberto would be, in your experience, Gilberto, what is the main challenge when you want to go from a server deployed solution to a cloud-based solution for a data cube that is managed, that is curated in time? What would you see as a main constraint? Thank you. You are muted, Gilberto.
The major constraint is the management, and what exactly you said. In a big area such as Africa, what happens is that that's lots of data, and you put in servers. And some of these servers, even though they're high reliable, they need backups. So they need backups, they need maintenance. And I don't think there is, let's say, maybe very, very large countries, like Brazil, China, are able to develop national solutions, or very rich countries such as Switzerland, national solutions that work for them. Now, I'm very much inclined to try to make the solution on Digital Earth Africa work. And by the way, let me just get one thing for Teresa. Teresa, there are two issues here. When we work, and specifically in Earth observation, there are two phases, very separate. One is the training, okay? What is the training phase? The training phase is where you get your samples, and then use an algorithm, random forest, to train the model. Okay. Once that model is trained, your samples are not necessarily required any longer. Therefore, in principle, you can train your algorithm, your model, in your local machine, and then deploy the model, not the data, to the cloud. And therefore, the cloud never sees your training data. What it sees, it's a model, but they don't see the training data that started the model. So there's no reason why you cannot use your local machine to train a model. Then you say, okay, I'm using this model to classify the cloud, in the data in the cloud, in which case no information goes out of the country in terms of sampling. And you still are able to use the cloud. So I still think that for countries that have restrictions on training data, that's a very possible and very simple and very workable solution. You don't have to export, there's no constraints there, because a model, you cannot deduce. The model works in such a way that you cannot deduce back the model from the training data, because the model already just simply has a set of weights or a set of methods. So you don't deduce the model from the training data. That's what so you don't need that. I hope it answers Lorenzo's question. You still are able to use Digital Earth Africa, but you don't export your training data. Does that answer your point, Teresa and Lorenzo?
Yeah, thank you.
And Teresa, if you want, I can show you how to do it. It's very simple.
Thank
The
you.
data nationalism. I think it will be a big problem in other areas also. The fact is that many national statistics offices don't want the data to go on a cloud or on a service. I don't know if there is any method to anonymize satellite data. This would be a solution. Otherwise, we'll have to still convince the legislators that this solution is safe, because it's a more legislative issue. So we need to convince them as statisticians that if we use this method, the data are safe and there's no risk of a breach of confidentiality. So it's a little tough. Yeah.
If I may chip in, there is new technology available in making the data readable just by the algorithm, but not by the user. It's called the differential privacy. So there are already this type of technology, which becomes a kind of plugin to your Earth observation data platform, so that when you want to train the algorithm, you cannot interfere with the data. You cannot read the data. It's just the algorithm that understands the data. So this is one one way to deal with it.
Okay, thank you. I think this is a lot to digest in 2 hours. So
there is a question for Crispin. So
is there another question?
Yes.
Or we can go to the health break.
It says, how do you deal with clouds, especially in the tropics? Should I answer it?
Sorry.
Yes, just Gilberto, please.
Okay, so essentially now what is happening in cloudy places, you have to rely on SAR data. There's no, I mean, in the mix of SAR data and optical data. And now, including that the new Sentinel-1C is going to be placed in orbit, SAR data can complement. Of course, as Lorenzo said, it's noisier, but again, there is useful data to be used in terms of SAR data. So there's no reason why. And in fact, SAR data can be used for these models as long as it's put on a similar data cube that you put optical data. So there is no serious problem here. Well, there is a serious problem with the clouds, but there is no impossible problem. In other words, there is no way you cannot do anything. No, yes, you can. And there are improvements, especially when SAR time series have proven to be quite useful for agricultural statistics. I hope I have answered your question, Crispin.
Okay, thank you very much. So we are going to take a 5 minutes break and come in 7 minutes. So it will be 4 o'clock in Addis. I don't know what time it will be in others. So thank you all and see you in 5 minutes.
Hello, everyone. I think the break is now over. We can now resume in a very few minutes when our presenters are back from the break. Okay, so we are going to have a next presentation from Eduardo Vasquez, and he's going to take us through the use of Earth observation data cube in Mexico to monitor agriculture frontier. So Vasquez, the floor is yours.
Thank you. Well, thank you, Teres. Can you hear me well?
Yes, correct.
Okay. I will share with you the works that we are doing at INEGI in the use of Earth observations to calibrate an algorithm to obtain the agricultural frontier in Mexico. This is an example of use of the data cube of INEGI to generate information of Earth observation for statistical agricultural information. Well, a short background. At INEGI, we began to use satellite images since 2009 to obtain the coverage of some crops in different conditions in the country. However, by that time, the satellite images, the cost of the satellite images were so high, and so we were limited to continue with this kind of projects. Also, as I mentioned in my presentation, in my introduction, INEGI is the National Statistic Office and is responsible to conduct all the agricultural censuses and surveys. And as a result of our previous agricultural census conducted in 2007, we get a shape file of the whole country with all the plots in the whole country. I am talking about 9 million of plots, individual plots, with the main activity. I mean, if there is agricultural, livestock, or forestry activity in these plots. This shapefile were updated in different projects, different projects developed after the census, and there was a combination of updating, asking the producers during the surveys, and also using satellite imagery to verify the activity, the agricultural activity on those plots. As a result of this activity, we get a map of the whole country with all the plots labeled with the main activity. We can see in this slide the Mexico shape, and all the green areas are the plots with agricultural activity. By the way, this is a good moment to talk about the concept of the agricultural frontier. We consider the agricultural frontier all the areas in Mexico that was used or have agricultural activity in the last 5 years. And as you can see, we identify, we discriminate, separate all agricultural lands from those that don't have agricultural activity. Other important thing to talk about is the implementation of the INEGI's data cube. In 2019, INEGI received advice from Geosciences Australia to implement the images data cube. Since that time, we were working in to obtain all the necessary implements, the infrastructure for the implementation of data cube. I mean, hardware, software, and humanware to realize and to implement to get the data cube in function. We began with the ingestion of the Landsat images. We get limited coverage of Mexico provided by the Geosciences Australia. And after that, our authorities get some agreements to get the Sentinel-2 images. Our data cube is now in construction, but it has some processes well implemented. And one of these processes is the integration of geomedian process. After the implementation of our data cube, some exercises were done to show our authorities, the utility of having this kind of information integrated in one place. What is the problem to solve? The problem is to produce reliable estimates of the national agricultural frontier using Earth observations combined with artificial intelligence algorithms. For that purpose, as I mentioned, we use our data cube that currently has around 38 years of information of Landsat images, but also we have now Sentinel-2 images around 7 years of information ingested in the data cube. We can see clearly that the Sentinel-2 has a better spatial resolution, and we use these images, the Sentinel-2 images, for this exercise of the agricultural frontier. Our objective is to calibrate an algorithm using artificial intelligence and Sentinel-2 imagery to estimate the national agricultural frontier. In the methodology, our data sources, our main data sources are the agricultural frontier obtained from the previous agricultural census, also a whole mosaic of Sentinel-2 images, but processed to get the geomedian of the whole country. The geomedian is an image that is free of clouds, but also include in the sources 20 spectral indexes related to different agricultural characteristics, and 48 texture filters that highlight different characteristics of the ground in the country. All this information is from the same age. I'm talking about all this information is from 2019. And as we saw as some slides before, our first source is the agricultural frontier, obtained and updated from the last agricultural census, where all the plots are labeled with the main characteristic of the activity in the plot. The second source is the geomedian, the mosaic of geomedian images that are built with the 12 bands of the Sentinel-2 images. And as I mentioned before, the geomedian is a result of a process that gives us an image free of clouds. We can see here a graphic description of the geomedian. In the light blue point corresponds to the same pixels in different images. This is the same area of 10 by 10 meters. And the dark blue point is the mean position of this pixel. But the mean position is affected by the extreme values. So we don't use the mean position, we use the geomedian that geomedian minimize the distance to each point or each pixel in the different images. And this is a very robust solution that allows us to obtain that image free of cloud. For the construction of the geomedian, we use the Google Earth engine. But the result of the Google Earth engine that is processed with the geometric median algorithm, the raw results should be reprojected and aligned to fit into this grid of 144 tiles to get the complete mosaic of the whole country. And as a result, we have a GeoTIFF image free of cloud with the 12 bands of the whole country. We also include 20 spectral indexes related to the agricultural characteristics. We have among these indexes, we have the NDVI, EBI, some well-known indexes that are related to the agricultural specific characteristics. And for the 48 texture filters, we used the infrared band. That is the most sensitive band to the agricultural information. And the filters were produced using the Loin-Malik texture filter bank, using a kernel, the 3x3 pixels, and to obtain the kernel to use it in the near infrared band to get the new filtered image. We can see here the result of some filters. As we can see, they highlight something special information about the ground. And when with these filters on and the indexes, we include more information to get a better training for the classification. We get 80 raster layers. We can see here the 12 bands of the Sentinel-2, the geomedian Sentinel-2, the 20 indexes, and some of the filters. All this information has a size of 17.2 terabytes. You can imagine the amount of information that will be processed or was processed. Once we had the geomedian, we made a segmentation of the information of the image in order to not to process every pixel of the image, but to process a group of pixels with the same characteristics. We can see here the segmentation, the polygons with pixels of similar information. And once we had the segmentation, we did the characterization of every segment obtained. Well, I will, okay. For all the segment, we get some information, maximum, minimum, average, the sum, and the standard deviation. And for the texture filters, we obtained the percentile 10 from 10 to 90. All this information, with all the information, we built an attribute table that contains 832 variables for each segment, classified in agricultural and non-agricultural. The segmentation gave us 261 million of segments. So you can imagine the amount of information that was processed. In this slide, we can see the whole process, beginning with the data, the image processing, the feature extraction, and the models used in the classification. We begin with the vectorial information, the lands with the labels, and also with the raster information, with the satellite images. And every step has the amount of information, and you can see that we are talking about gigabytes, terabytes that are adding space in the process. We did the segmentation, we obtained the spectral indexes and the texture filters. After that, we did the feature extraction to construct the big table of 832 variables. And after that, we use different algorithms to process the information, to training and process the information. But the tree with the best results was extra trees, random forest, and multi-layer perception. And from the three algorithms, the best with the algorithm with the best solution was random forest with 86% accuracy. However, for the final result, after the training, we use two different processes. One with the training the whole country with just one training information, and we did other results training the algorithm with different regions, because in the north part of Mexico, there are places with desertic characteristics, and in the south part and the central part are more water, more humidity. So there are different characteristics, and we train the algorithm with this difference. And you can see we get a better result using a regional training for the algorithm. We get a 21% of accuracy. And after that, we construct, we get a map with the results. In this slide, we can see the different processes with the different processes in all the of the methodology, and highlighting the I lost the word. Highlighting the different steps, different the different steps used in the whole process, and times. We began with the processing server and the directory preparation. We obtained the geomedians. And after the geomedians, we did the processing to prepare information. And after that, we did the alignment and the reprojection of the information to fit into the grid for construct the whole mosaic. And after that, we did the segmentation. This process was a very hard process that took around six days to get the final results. Also, when we processed the sub-indices, it was. Can you hear me well? Because I'm okay.
Yes.
Okay, I'm back in the presentation. Well, the generation of the indices was a process that was very fast. It took 1 day. And for the texture filters, it was also a very hard process that took around 7 days to get it. So this map shows all the work that we did to obtain the classification. In the results, we can see here in the results 2 rounds of Sentinel-2 images compared with the reference information that is the green column. And we have here the result with 21% of accuracy, but also we ran a process with images of 2021 using the same label information of 2019 that will be validated with the results of our recently released agricultural census conducted last year and released 2 weeks ago. So we will work in these days to validate this information and to obtain the accuracy of the results. Also, we get this map, this kind of maps. The random forest give us an information that is the certainty measure that give us the certainty that we have in every result that we can see here. We can see that the 33 hectares of the results of this table corresponds to a certainty measure of the result of 55%. So we think that we need to work a little bit more to get a better certainty measure result. And we are working in this topic. As part of the results, our colleagues of Data Science Laboratory create a web application to see the result using a base of satellite images, and to verify the results obtained and check where the algorithm has differences or is the result is not too good as we expected. And another application that was created is WMTS that allows us to use the layer of the result to compare with our layers of informations previously obtained, and compare also to detect some differences and to identify what we need to do to refine or recalibrate the algorithm to get better results. Our next steps, we have now a new run that was conducted using information that fits or corresponds with the period of the agricultural census, that is October 2021 to September 2022. And this result will be compared with our agricultural census results released, and we will to identify these areas with good and poor algorithm performance to refine the algorithm and get better results. As a conclusions, we have that we think that this is a very good, successful collaboration example, because this exercise was developed by different areas at INEGI. The geographic area was in charge of getting all the satellite imagery, and the computing area of INEGI was in charge of getting and implementing the data cube. Our data sciences laboratory colleagues were in charge of the processing information, and the area of the agricultural census and surveys, we are validating the information, and we are working together to complete this algorithm. We are using open data that allows us to replicate this methodology in any moment with any data set of images. And also, as we can saw during the presentation, this is a good example of big data. You saw we can saw the amount of information that was processed, and the results are relevant because once we release the final algorithm, we will be able to monitoring the agricultural frontier, because this is an important information. The agricultural frontier will be used as a reference space of agricultural area for our next statistical events, like surveys or our next agricultural census. Well, thank you, and if you have questions, I'd be glad to answer you.
Thank you, Eduardo. This was really informative. You have taken us through the experience at INEGI and how collaboration benefited the actual results at the moment. I only can see one question in the chat. Maybe others feel free to raise your hands. There is a question: why is the geomedian? Is it possible to find out the law of median in statistics?
Well, we use the geomedian because it allows to get a complete mosaic with of the image free of clouds. That was the main reason, because Mexico is located in some place where the main cycle of production is affected by clouds. Our main cycle production is between May and September, and in this period of time, we have a lot of clouds in the country, and we use the geomedian to get this free of clouds mosaic.
Okay, thank you. I don't see any raise of hands. I think we can move on. Yes. Florenzo, do you have a question?
Just want to have a question. Eduardo, do you see in the agricultural frontier, do you see the integration of farmer data submission through apps to enrich the training data, or to enrich, let's say, the survey-based activities? Do you see this activity in the future, or maybe you're already engaging into that? Just, I'm curious to learn about the role of farmers within those contexts where the agricultural statistics seem to be quite advanced using geospatial data. Thank you.
Thank you, Lorenzo. Well, this kind of collaboration of the farmers is not implemented by now in the country, at least not at INEGI. There are offices in the agricultural ministry that has a close relation with the producers, with the farmers, and maybe in the future we can implement some kind of this collaboration. By the moment, we go to the field and ask to the farmers. One of the projects that updated the shapefile was the agricultural frame updating conducted in 2016. We went to the field and asked every farmer for the information for their plots.
Thank you, Eduardo. Thank you for the presentation. And I think for participants who want to get in touch for later, feel free to, I can see one comment from Zuve. Did Mexico conduct a complete census? The algorithm seems to be a good replacement of post-enumeration survey.
Yes, we have finished we complete our census last year and released the information this year. However, I consider that it cannot replace this exercise cannot replace the enumeration, because it is only focused on the agricultural activity, and the census includes the cattle information and forest information. So by now is focused only in the agricultural. Maybe for this segment can be used, but not for the whole agricultural census.
Yeah. Thank you. So we are going to have our last presentation. Actually, it's not a presentation, it's a demo. I know we have had a lot of information to digest today, but we are going to have now a demo on Earth observation start crop mapper in Senegal. So I'd like to hand over to Vivian Ondeki to take us through.
Oh, okay. Hi, everyone. So I actually had prepared a small presentation just to give an overview of how the methodology for the tool works. So I'll just be very brief, and then afterwards I can jump to the demonstration. Okay, if you allow me to share my screen.
You don't have rights to share?
Just a minute, just to check.
Okay.
Can you see my screen now?
Yeah. You can put it in presentation mode.
Presentation. Okay, great.
Yeah, perfect.
So thank you, Therese. So I'm going to demonstrate to you the FAO open source tool for crop mapping. And this demonstration will be focused mainly in Senegal. So before that, I'll just take you through the methodology of how the tool works. And then afterwards, I'll go to demonstrate. So Lorenzo has already given an overview of the project. And also Gilberto has mentioned on the issue of big data error. So we've seen these big volumes of Earth observation data. And for instance, in the recent times, Copernicus has, one of the largest space providers is currently releasing data, 16 terabytes of data per day. So additional to that, you can see this image in the next year, how many satellites are still planned to be launched from now to 2030. And we also have availability of computation facilities, such as Amazon Web Service, Google App Engine. However, these they're not operationally used for crop monitoring, especially in developing countries. So this is where EOSTAT project comes in to try to, support countries to automate this task, to automate crop monitoring tasks in terms of continuously collecting agricultural statistics, integrated with Earth observation data, and through fiscal modeling and data ground truth data collection. Additional to that, we have research whereby we are trying to test data fungal algorithms such as DTW, transfer learning, with an overall aim of supporting accurate reporting and, to enhance improved food security monitoring. So why do we do crop type mapping? Of course, this is not new to anyone. Crop production is a major source of food in the livelihood, and there's need for regular and granular crop information to improve food security and food production. Therefore, remote sensing offers easier way of generating crop statistics. And in this course, you will learn how to use Earth observation data for crop monitoring. First, one objective is to, first of all, take you through the methodology, and then afterwards you learn on how to use the tool, whereby you can select a study area, define crop calendars, perform quality check of your in-situ data, run a supervised classifier, and also be able to explore your results using Google Earth Engine tools. So the tool offers a supervised means of classification, whereby you have your training data from the field, and then you set a part of the training from the data from the field for training your model, and another for validation. So in this sense, this field data is associated with the spectral signature, which helps you to analyze different properties of the ground. So it's essential to have, it's very important to have location accuracy when collecting the field data, and also making sure that your labels have correct labels and also are coherent to the spectral signature. Okay, so the first step you need to use the tool is to first define the region of interest. And this essentially helps you to, select the focus area of interest that you can work with. So the tool in this case allows you to use, to select region of interest where you can integrate agroecological zones and also the district level. So it also allows you to upload your own data, and this needs to be in a specific format. We even have a manual for this, which can be shared. The second step is quality check of the in-situ data. This essentially allows you to ensure there is location accuracy. The points are consistent with the label. For example, you have different crop type information. They should be consistent with what is exactly on the ground. For instance, this image you see, there's a point in the cropland which seems, if you're mapping a specific crop type, it shows that you compare the point, the selected. Okay, sorry. Current slide. Is it okay now, or do you need? It's okay.
You have to launch it in presentation mode. You launch presentation mode
From current slide.
No, is it not?
Really?
You can see your next slide in the comments.
Okay, sorry for that. I realized I was sharing. So I'm just trying to share with the presentation mode.
Yeah.
So let me just close the screen and share again. Maybe they also would. Okay. Content. Current slide. Is it okay now?
Not doing presentation. Can I help you?
Yep, of course.
Because you need to. So which screen do you have the presentation? On this screen here.
Yeah.
Okay. No, maybe here you can this last maybe.
Okay. So
Seems to me this is the other screen, right?
yeah.
Okay, so maybe if you can measure again. That is screen number 2, right?
Yeah.
Here's screen. This is screen number 2. Okay.
Yeah, it's great now.
It's okay.
Yeah.
Okay. Okay. Thank you for letting me know and apologize for the. So we can go ahead. I think I was explaining on this slide. So as I mentioned before, the first step you require to use the tool is to select your region of interest. And this way you can load it allows you to select the agroecological zone as well as, the district. And you'll also be able to load your in situ data. And the second step is to verify your points, whereby given the in situ data, you can ensure that there's the signatures, the mean spectral signature of the point, and for instance, you have different crop types, let's say maize, and you want to compare the point with the mean spectral signature of maize crops. So it will indicate on your right here, step 3, you can see a chart with the selected point in black, and in blue is the average signature of maize for all the points. So this way it allows you to ensure there's consistency of the spectral signature with the label. And then the third step, you'll have to prepare your satellite imagery. And to do this, you need to know the crop seasons. So since we're interested in the crop-specific temporal metrics that are related to crop phenology, here we are looking into extract information from preparation of the soil, maximum NDVI growth, and also towards harvesting. So having a crop calendar, which is provided by FAO, helps you to design to select the specific season. We also have a chart of the rainfall, and which gives you an idea when is the rainy season, when it occurs. So this information can also be added while in the field. For instance, you're in the field, you can add this information in your in situ data. For instance, in Senegal, we have 2 crop growing seasons. We have the rainy season and we have dry season. So most farmers grow crops during the rainy season. And during dry season, we have crops mainly which are grown through irrigation. And once you have your season, your period of crop growth, you also have an option. The tool allows you to select different sensors. For instance, we have a combination of Sentinel-1 and 2, and you also have an option to select Sentinel-2 data only. So for instance, in areas where we have cloud coverage for a longer period of time during the crop growing season, Sentinel-1 can help you to improve your model performance in classifying the crop types. So, of course, we all know that before images can be analyzed, there's need of some degree of pre-processing, which is necessary to correct any distortion in the images, for instance, clouds. So this shows an exploration of a region in Dakar, Senegal, whereby from June 14th to November 30th, different images across the growing season. So you see there's a lot of clouds, and there's needs to generate harmonized time series, which can also capture the various phenological stages of crops. Additionally, we find that with the satellite imagery, due to the revision time, we find that some images are captured in a specific dates. Some regions have images captured on later days. So there's need for, creating some sort of a harmonized regular time series that can be used for machine learning. So next slide. So how do we process our images? First of all, we have, for instance, for Sentinel-2 images with the clouds, we perform cloud masking using Sentinel-2 Cloudless. And then to fill the gaps in the masked images, we perform interpolation, and we have two options for interpolation. We have linear interpolation and fitting an harmonic model to the time series. This allows you to generate image that is gap filled. It also reduces the size. As a result, we have a data cube generated for a specific season as a specific region. And then once you have prepared your image, the next step is to derive the crop map. And there are two algorithms that are, options in the tool. So we have time-constrained dynamic time mapping, like Giboto has mentioned before, which is a pattern recognition method. And then we also have random forest classification, which is the ensemble learning method. So the final step is to visualize it and download the results. So this is just a methodology of how the tool works in performing crop type mapping. But to just give you an overview of how the tool is designed, it has two components. We have the admin tool and administrator tool. And these tools are also dependent on different crop library and asset folders. It's also important to know that this tool can be adapted to any other country which have specific crop information. And the admin tool allows you to, it's specific for generation of crop type map. And this is how the interface looks like. So this tool is specific for an expert who can generate a crop map. And the end user tool is more on the end user. It's just a dashboard where you can visualize your generated crop map. The application architecture is designed in a way that the user provides inputs to the Earth Engine, and then in the backend, the Earth Engine finds the results and feeds them back to the app interface. So thank you so much. This is just a short presentation. I'm open to questions, and then I'll show the demo on how the tool works. So I'm opening 5 minutes period for questions. Thank you.
Thank you, Vivian. At the moment, I don't see any question in the chat. Yes, I can see one hand raised. Please go on, Mamadou. And then Isufu.
Thank you, Vivian, for your presentation. So I will not be able to go long. I ask the same question with, do you work also with in collaboration with DAFSA also?
Mamadou, please go ahead with your question.
Yes, I say you work even in collaboration with DAFSA also in your modernization. That I have that question. Only question. That's the question. You understand? You hear me?
Thank you. Thank you for your question. Yeah. So you just asked if we're in collaboration with ESA. Did I get that right?
With DAPSA, yes.
Yeah, not in this specific project, this specific work. So we have other collaboration, but for this tool, it's mainly for FAO. Hope
Okay,
I answered. Yeah.
Okay, I see. But what you have developed in your presentation is need by DAPSA. So I ask the question. Thank you for that.
Okay, thank you.
Isufu, was your hand by mistake or you want to come in?
Yes, I just wanted to ask the relation with the National Statistic Office. So are they seeing these data are country produced indicator, and are they accepting to take it as input in the statistical production, or you are still at an experimental stage where you need to convince them that it is a valid methodology? Over to you.
Thank you for your question. So the tool is in a deployment stage. It can be applied for different regions. So currently we are using adapting the tool for Zimbabwe crop type mapping, summer crops. And it's, as you can see from the demo, it's a tool that can be used for, any other country. We even have a manual that can be followed and be adapted for crop type mapping for other countries.
There's another question in the chat. What kind of crop information would you say we need to have in order to explore this tool?
So, of course, you need the data from the field, since it's a supervised based classification methodologies. So you need in situ data from the field. This is just GPS location, or to indicate the specific crop type information, and then this is what will be used as an input for the tool. I hope I answered.
Yeah, no more questions so far. Maybe you can go on with the demo while people, please, all the participants, feel free to even write in the chat if you have more questions.
Okay, thank you, Teres. So I will address more questions after the demo. So I will share my screen. Let me know if you can see.
I think at the moment we can see your desk, but we can't see the applications. We only see the desktop background.
Okay, the desktop. How about now?
Yes, it's now coming. Yes, perfect. Yeah.
Okay, so this is the interface of the crop admin tool. So we first have a panel for where you can add your inputs. And for instance, you've collected some samples from the fields, you uploaded in your Earth Engine asset. You'll be able to load it. Sorry, I'll just kind of, because I'm using two screens, so I think it's more comfortable if I just use one screen.
This is not a screen right now.
Yep, just a moment. Sorry. So I'll share the screen again. Can you see my screen?
Yes. Yeah.
Great. Okay. So this is the admin tool. So of course we have the script for a specific country. In this case is Senegal. And we have a panel here whereby you select your signatures. So for instance, I select one of the crop signatures that these are in situ samples collected from the field that you have to format it to have a specific format so that the model can read it. And then I select the agroecological zone in the district. And then I search, you also select the season, crop season and the year. And then you search for samples. In the back end, it's going to plot all the points on the map. So on your right side of the screen, you'll see the chart showing the distribution of the points of different classes. And also it will show you the spectral signature of each crop type or land cover. So, so we have all the points plotted. So please note that these points are, some of them are verified, the green ones, so the red ones are not verified. So just for illustration, we have plotted all the points. And for instance, like I said, the tool allows you to verify points based on the location accuracy, the crop type label consistency, and also consistent with the spectral signature. So for instance, I select maize. It will take me to this point where maize is located. And to know which point is selected, it has a circle, black circle on the point. So, so it's generating a chart of the points. This will take a bit of some time. So here we have the mean individual signature of the point compared with the mean of the other maize points. So this way you can check if the signatures are similar. If they are not the same, you can, it depends on your judgment if you're sure that this point is correct or not. Of course, when you go into the field, you have a lot of errors sometimes. And so this tool enables you to verify this. So if you check on the point, you can decide to, change the attributes if you're not sure if, if, for example, let's say we can try an example here. Let's say I remove this point. You can always change to satellite mode to have a more resolution image in the background. So for instance, if we select maize 0.5, it will take us to the location and the signature will be plotted on the right side of the screen. So for instance, if I want to compare the signature, it's loading on the right side. And if you want to change the coordinates, let's say it's falling on top of a house instead of cropland, because in some areas in Africa we have houses and cropland, it's, it's very heterogeneous. There's a house inside a crop area in a village. So you find that somebody might have put a point on the house, or like just some small error. You have an option to remove the point by selecting remove point. As you can see, the point has been removed. And we also have an option to change coordinates. And this can be in cases where you find a point is falling on forest or urban area, and it's, it's indicating as a different class. So the tool takes a while to reload. For example, if I remove that point, it will update on the back end on the existing locations. So let's select another class, for instance, forests. So here, forests is 2.7. And on the right, it will compare the mean spectral signature of the forest class and the selected point. So it's generating the chart here. You can see this point is, kind of, it fits well with the mean forest curve. So in this case, I can choose to keep this point. But in cases whereby you want to, change coordinates, for instance, I don't have a good example where the point is falling on a wrong class, but just for information, it's possible to change coordinates by selecting the change coordinates tool. And then you can select any other area, for example, here. So it has shifted to this class. And then you say, okay, so we have to note the name of the sample is forest 327. Select okay. And then you can verify this to, for example, change the name to a specific crop class, or, if you're very sure that this point is that class. So since I don't want to change this, I just cancel, and I'm not sure what this point is. So it's just to show you how the tool has the flexibility of changing the the attributes, or removing points that are not consistent to the spectral signature. So in this case, I'll just change the coordinates back to where it was. So I'll just put it back there and say okay. Okay, so in this process, you can do this for several points. For example, it's specific for which kind of algorithm you want to generate the crop class. And after you're sure you verified the specific points you want, you can update the library. And the tool will ask you if you want to update the existing crop library. So it will generate a crop library with the verified points. And these verified points will be used for training the model, and the rest of the points will be used for validation. In this case, for DTW model, I would advise to use at least 5 samples per class. Random forests, you can always increase the number of samples. So it will also ask you to agree to export the updated crop library. And here it will show you the exporting status. So pending is showing it's exporting in the background. Once it's finished exporting, it will show, it will write succeeded. So we have to give it some time. Usually takes like 2 minutes, 3 minutes. And then it also depends with the size of data you're exporting. Okay, so it's showing it's exported, and then automatically the points that you've exported will be used for classification. So you see here the signatures have changed. It updates automatically on the user input. So after that, it shows how many samples you verified. In this case, 83 samples for different classes. And then here you can select the method of crop map generation. Like I mentioned, you have DTW, random forest, and then the number of samples you use for each class for training your model. And then the sensors to use. We have Sentinel-1 and 2, and option Sentinel-2 alone. So after that, you export the crop map. It will also still ask you if you want to update the existing asset with the new crop map generated. So you just say, okay, you finally finally give a final okay. And then this will display on your task manager here, where you can finally run your export. And that way it will be exported in the asset. So to just display, I think there's some time. Okay, so here it shows the image you're trying to export, and you just say run, and it will automatically go to your asset. So you just say run. So normally it takes some time to export the image, but just note, once you've customized the tool to a specific region, you don't need to code anything. You just input your input, and then you just verify your points, and then generate a crop map based on specific inputs that you need. And then this image will be exported in a file format that will be automatically being read in the end user tool. So like I mentioned before, the end user tool is just an application, and it has a panel where you define your inputs. And in our case, we assume that we have exported the map asset, and then we now filter our classified output based on this variables. So in this case, I'm looking for an image that I classified with the rainy season in 2021 using Sentinel-2 image, and the method of classification is DTW. Of course, you can always change to random forest. And also, if you classify with dry season, you have an option to select all that. So you click submit. So the tool is currently looking for available images, and a pop-up will display showing the existing classification outputs. And I'm going to load the most recent one on 7th December. And this will also show you the number of samples that we use per class for training, and if there's available samples for validation. In this case, I use 6 samples per class for training, and the data I last updated was December 7th. So I load that one and say okay. So the tool will enable you to visualize the results. As you can see on the map, we also have ability to check the legend. We have vegetation, no vegetation, water body, maize, millet, groundnuts, and cowpeas. On the right side, you can also explore the different crop area statistics, and also a distribution table showing you how much area is occupied for a specific class. We have a validation panel whereby with the validation data set, you can evaluate the model performance. And by clicking on that pop-up, it will show you the classification accuracy, and also we'll be able to see which points were correctly classified on the map, and which ones were not misclassified. And the tool also allows you to, so we still wait, so we can see this pop-up showing the different accuracy. We have the kappa accuracy, we have producer and consumer accuracy for each class. And based on this, you can always want to improve the model, or, so you also have an option to download the map. And this map is downloaded in tiles. So this, when you click on the pop-up open crop map download panel, it will generate another pop-up where it will ask you to select on the tile that you need to download. As you can see, we have 2 tiles for Nioro. So in this case, the spatial resolution is 10 meters. So I select on this specific one, and it will generate a URL where when you click it, it will lead you it will download automatically the classified image for that tile. So it's still loading. It depends on the connection.
Sorry, Vivian.
Yeah.
Apologies to interrupt. Do you still need more time? Because we have now gone past time, 17 minutes past time. So we need to wrap up.
Sorry for that. Yeah. So yeah, actually I've just finished. So that's the downloaded map. You can choose to visualize in QGIS or further process. Thank you. Apologies for taking extra time. So yeah.
You are muted, Teres.
Oh, sorry, I've been speaking. Sorry,
Yeah.
I was saying this is really insightful, and that's why you couldn't even finish. I think participants are eager to navigate the tool and experience from their perspective. So I want to check whether you can share the link and participants start to check the tool. Also, there are quick questions in the chat. How can the tool deal with the climate change that affect the crop phenology?
So from what I understand, so the tool allows you to generate crop type maps, and based on the crop phenology, such as start of season, end of season, you can be able to, decide the period of, growth season, which will enable you to use for generating your satellite time series, and finally perform classification using a supervised classifier. So in terms of climate change, I'm not sure I understand the question, but in terms of phenology, you can use this information to use the tool to derive your crop type map.
I can see Lorenzo Hans. Do you want to come in? Yeah.
Hello. So if I may chip in regarding the question on how do we handle with the climate change and climate anomalies. So in the tool, there are 3 types of algorithms available out of the box. One of these is the dynamic time warping, and it's a time-weighted dynamic time warping. So we've allowed 30 days to the model, 30 days of shift between the time series alignment to account for late onset of the season, for instance. Of course, we need to verify the results in order to understand how the model is able to forecast, to recognize the crop type in a different year, let's say. But I would like to say that the advantage of this type of approach is that you don't need a lot of training data for each crop type. So we see it a sustainable practice to gather 5 to 10 data points for each crop, for each agricultural season, so that the tool is able to map the crop types with a higher accuracy. And then I wanted also to add just a small thing that in the presentation of Viviane was not possible to elaborate because of the time. So consider that when the user is checking for the crop signatures, like she showed, when she's quality controlling the in situ data, you could see that in the chart, you could see the signature. I just wanted to highlight that the system has already pre-processed the data cube. So it's already done on the fly. And of course, it's optimized for the agricultural calendar of the country. And this is a great advantage because essentially you don't need to take care of the pre-processing because that's already inbuilt. Just wanted to highlight that. Thanks.
Thank you, Lorenzo. There's another question from Nyapwele from Newton, if I'm pronouncing it well. Thank you for the presentation. Is there a time in future when we not need a supervised classification, but instead an unsupervised classification when the same area is run every year? And maybe you can respond together with the next one. Does the tool work only on points or can use the crop field polygons to generate signatures? Back to you, Lorenzo and Vivian.
Okay, so I didn't get the first question. Sorry.
The first question was, is there a time in future when we not need a supervised classification, instead an unsupervised one, when the same area is run every year?
Maybe I can take this one. Okay. So, well, that's the ideal scenario that automation is looking for, when you don't need to go to the field anymore and you are able to detect. Of course, artificial intelligence is providing this type of vision. I don't see yet a system that is capable of doing that nowadays, but I believe that by establishing a consistent baseline, so consistent training data for a country for several years, then I tend to believe that deep learning, like the temporal convolutional neural network that Gilberto Camara presented, I think that could be it could offer a solution, at least for national level. I don't know what is Gilberto's view on the feasibility for something like that. Thank you.
Thank you, Lorenzo. Well, I think that the main point here is that training data in the end is user knowledge. So in that sense, it's hard to replace training data with completely automated tools, unless these automated tools have by themselves already been quite successfully, let's say, trained with pre-trained data, which is, for example, the case of ChatGPT. So enormous, think about ChatGPT, enormous training data set, trained with the words, our words, Wikipedia and whatever we wrote, and still it hallucinates a lot. So I think we should not underestimate the importance of training data, which conveys the situation that maize in Senegal will be different from maize in Zimbabwe. And that if I know how to classify maize in Senegal, the Sahel, the whole variation, huge variation year to year, may not fit the Zimbabwean maize. So I'm very careful now, because even the successes enormous of artificial intelligence that we have seen are successes which are based on massive, massive, massive training, massive amounts of data. So I would be careful, while not ruling out anything in the long run. Okay, in the long run, anything is possible. But in the short run, it's like 5 years, I don't see an automated tool, unless this automated tool has been fed with so much data from our countries that it's like ChatGPT, it would work. But again, you're back to the problem that it needs to be fed with training data. So I don't see in the current trends anything that will get us completely away from training data. We may be more effective at using whatever data we have, which is different. Thank you.
Thank you, Gilberto. There is two couple of questions again. Thank you for the presentation. Is the app available for the public?
Yes. Okay, so the app is available to the public. I put it on the last slide of the presentation. Maybe I can just share with you in the chat. It'll be easier to access it. Okay, so I've just shared the link of the application in the chat.
Yeah, thank you. And there's another question from Alex. Does the tool work only on the points, or it can use the crop feed polygons to generate signatures?
So thank you for your question. Currently, the tool is using points, basically because of easy computation. But of course, if needed, it can be integrated with polygons as well. This way, but also it has challenges. For example, in developing countries whereby the crop type information is we find a plot with several missed crops, and so it's difficult to really label this per polygon. So that's why the easiest option was to go with the points. And for example, the DTW algorithm, it's very sensitive to accurate spectral signatures. If you have information that is not, pure signal, it will not perform that well. So that's why we are using points at the moment. Yeah.
Thank you. And I think one last question is from Mamadou, who was asking whether you are trying to validate the models using in situ data.
Yes. So yes, Mohammed, we are using in situ data for validation. Like I showed in the tool, we have samples that are used for validation and others for training. So yeah, it's a very essential step in the whole process where we validate the model.
Thank you very much for our presenters. If we were in a room, I would ask participants to join me to thank you all, but we can always do that using our reactions. Thomas summarized it and saying it's an eye-opener for everyone. And he was asking for presentations. To mention that we are sharing the slides afterwards, and the recording will also be available at the Regional Hub website. I've shared the link in the chat, but also I saw that Gilberto already has shared the link to his presentation, and others are following. Thank you for everyone who attended, and our presenters. I think we thank you that you have already shared your contact details. If a country wants to reach out to you, we thank you for that, and we always count on your support. Thank you very much.
Thank you.
Thank you all.
Thank you. See you.
Thank you.
Thank you.
Bye.
Bye.